In mathematics, the unitary group of degree n, denoted U, is the group of n times n unitary matrices, with the group operation that of matrix multiplication. The unitary group is a subgroup of the general linear group GL. Hyperorthogonal group is an archaic name for the unitary group, especially over finite fields. In the simple case n equals 1, the group U corresponds to the circle group, consisting of all complex numbers with absolute value 1 under multiplication. All the unitary groups contain copies of this group. The unitary group U is a real Lie group of dimension n2. The Lie algebra of U consists of n times n skew Hermitian matrices, with the Lie bracket given by the commutator. The general unitary group consists of all matrices A such that AA is a non-zero multiple of the identity matrix, and is just the product of the unitary group with the group of all positive multiples of the identity matrix. Properties. Since the determinant of a unitary matrix is a complex number with norm, the determinant gives a group homomorphism. The kernel of this homomorphism is the set of unitary matrices with determinant. This subgroup is called the special unitary group, denoted. We then have a short exact sequence of Lie groups. This short exact sequence splits so that may be written as a semi-direct product of by. Here the subgroup of can be taken to consist of matrices, which are diagonal, have in the upper left corner and on the rest of the diagonal. The unitary group is non-abelian for the center of is the set of scalar matrices with. This follows from Schur's lemma. The center is then isomorphic to. Since the center of is a dimensional abelian normal subgroup of the unitary group is not semi-simple. Topology. The unitary group U is endowed with the relative topology as a subset of M, the set of all n times n complex matrices, which is itself homeomorphic to a 2n, two-dimensional Euclidean space. As a topological space, U is both compact and connected. The compactness of U follows from the Heine-Borel theorem and the fact that it is a closed and bounded subset of M. To show that U is connected, recall that any unitary matrix A can be diagonalized by another unitary matrix S. Any diagonal unitary matrix must have complex numbers of absolute value 1 on the main diagonal. We can therefore write a path in U from the identity to A is then given by the unitary group is not simply connected. The fundamental group of U is infinite cyclic for all n. To see this, note that the above splitting of U as a semi-direct product of SU and U induces a topological product structure on U, so that now the first unitary group U is topologically a circle, which is well known to have a fundamental group isomorphic to Z, and the inclusion map UU is an isomorphism on pi1. The determinant map det. UU induces an isomorphism of fundamental groups, with the splitting UU inducing the inverse. The WEYL group of U is the symmetric group Sn, acting on the diagonal torus by permuting the entries. Related groups. 2 out of 3 property. The unitary group is the threefold intersection of the orthogonal, symplectic, and complex groups. Thus a unitary structure can be seen as an orthogonal structure, a complex structure, and a symplectic structure, which are required to be compatible and ensures compatibility. In fact, it is the intersection of any two of these three, thus a compatible orthogonal and complex structure induce a symplectic structure, and so forth. At the level of equations, this can be seen as follows. Any two of these equations implies the third. At the level of forms, this can be seen by decomposing a Hermitian form into its real and imaginary parts. The real part is symmetric, and the imaginary part is skew-symmetric, and these are related by the complex structure. On an almost Kähler manifold, one can write this decomposition as H equals G plus I omega, where H is the Hermitian form, G is the Riemannian metric, I is the almost complex structure, and omega is the almost symplectic structure. From the point of view of Lie groups, this can partly be explained as follows. O is the maximal compact subgroup of GL, and U is the maximal compact subgroup of both GL and SP. Thus the intersection OGL or OSP is the maximal compact subgroup of both of these, so U. From this perspective, what is unexpected is the intersection GLSP equals U. Special unitary and projective unitary groups. Just as the orthogonal group has the special orthogonal group SO as subgroup and the projective orthogonal group PO as quotient, and the projective special orthogonal group PASEO as subquotient, the unitary group has associated to it the special unitary group SU, the projective unitary group PU, and the projective special unitary group PSU. These are related as by the commutative diagram at right. Notably, both projective groups are equal. PSU equals PU. The above is for the classical unitary group, for unitary groups over finite fields. One similarly obtains special unitary and projective unitary groups, but in general, G structure, almost Hermitian. In the language of G structures, a manifold with AU structure is an almost Hermitian manifold. Generalizations. From the point of view of Lie theory, the classical unitary group is a real form of the Steinberg group, which is an algebraic group that arises from the combination of the diagram automorphism of the general linear group and the field automorphism of the extension C, R. Both these automorphisms are automorphisms of the algebraic group, have order 2, and commute, and the unitary group is the fixed points of the product automorphism, as an algebraic group. The classical unitary group is a real form of this group, corresponding to the standard Hermitian form psi, which is positive definite. This can be generalized in a number of ways. Generalizing to other Hermitian forms yields indefinite unitary groups U. The field extension can be replaced by any degree 2 separable algebra, most notably a degree 2 extension of a finite field. Generalizing to other diagrams yields other groups of Lie type, namely the other Steinberg groups and Suzuki-Re groups. Considering a generalized unitary group as an algebraic group, one can take its points over various algebras. Indefinite forms analogous to the indefinite orthogonal groups. One can define an indefinite unitary group by considering the transforms that preserve a given Hermitian form, not necessarily positive definite. Here one is working with a vector space over the complex numbers. Given a Hermitian form psi on a complex vector space V, the unitary group U is the group of transforms that preserve the form. The transform M such that psi equals psi for all V, WV. In terms of matrices, representing the form by a matrix denoted phi, this says that M phi M equals phi. Just as for symmetric forms over the rails, Hermitian forms are determined by signature, and are all unitarily congruent to a diagonal form with P entries of 1 on the diagonal and Q entries of -1. The non-degenerate assumption is equivalent to P plus Q equals N. In a standard basis, this is represented as a quadratic formers, and as a symmetric formers. The resulting group is denoted U. Finite fields over the finite field with Q equals PR elements, FQ. There is a unique quadratic extension field, FQ2, with order 2 automorphism. This allows one to define a Hermitian form on an FQ2 vector space V, as an FQ bilinear map such that M for C FQ2. Further, all non-degenerate Hermitian forms on a vector space over a finite field are unitarily congruent to the standard one, represented by the identity matrix, that is, any Hermitian form is unitarily equivalent to where represent the coordinates of W, VV in some particular FQ2 basis of the n-dimensional space V. Thus one can define a unitary group of dimension n for the extension FQ2, FQ, denoted either as U or U depending on the author. The subgroup of the unitary group consisting of matrices of determinant 1 is called the special unitary group and denoted SU or SU. For convenience, this article will use the U convention. The center of U has order q plus 1 and consists of the scalar matrices that are unitary, that is, those matrices CIV with. The center of the special unitary group has order GCD and consists of those unitary scalars which also have order dividing n. The quotient of the unitary group by its center is called the projective unitary group PU, and the quotient of the special unitary group by its center is the projective special unitary group PSU. In most cases, SU is a perfect group and PSU is a finite simple group. Degree 2 separable algebras. More generally, given a field K and a degree 2 separable K algebra K, one can define unitary groups with respect to this extension. First, there is a unique K automorphism of K which is an involution and fixes exactly K. This generalizes complex conjugation and the conjugation of degree 2 finite field extensions, and allows one to define Hermitian forms and unitary groups as above. Algebraic groups. The equations defining a unitary group are polynomial equations over K. For the standard form template, the equations are given in matrices as AA equals I, whereas the conjugate transpose, given a different form, they are A phi A equals phi. The unitary group is thus an algebraic group, whose points over a K-algebra are given by, for the field extension C, R and the standard Hermitian form. These yield an algebraic group with real and complex points given by. In fact, the unitary group is a linear algebraic group. Unitary group of a quadratic module. The unitary group of a quadratic module is a generalization of the linear algebraic group U just defined, which incorporates as special cases many different classical algebraic groups. The definition goes back to Antony Bach's thesis. To define it, one has to define quadratic modules first. Let R be a ring with anti-automorphism J, such that for all R in Rn, define let lambda R be an additive subgroup of R, then lambda is called form parameter if n, a pair such that R is a ring and lambda a form parameter is called form ring. Let M be an R module and F a J-Sesky linear form on M. Define M, then F is said to define the lambda quadratic form on M. A quadratic module over is a triple such that M is an R module and is a lambda quadratic form. To any quadratic module defined by a J-Sesky linear form F on M over a form ring, one can associate the unitary group, the special case where lambda equals lambda max, with J any non-trivial involution. Polynomial invariants. The unitary groups are the automorphisms of two polynomials in real non-commutative variables. These are easily seen to be the real and imaginary parts of the complex form. The two invariants separately are invariants of O and SP. Combined they make the invariants of U, which is a subgroup of both these groups. The variables must be non-commutative in these invariants, otherwise the second polynomial is identically zero. Classifying space. The classifying space for U is described in the article classifying space for U.